Okay, good afternoon, everyone. Thanks for coming to this session. So we in the next hour or so we have two talks, one by myself and one by my colleague Ravi-Madduri. So we're going to be presenting on two different aspects of the problem or opportunity of, as we say, science as a service. So as we'll explain, we have been working for some time now at the University of Chicago and Argonne National Lab on seeking to accelerate discovery across a range of scientific disciplines by taking the activities that end up being time-consuming in science, especially big data science, and delivering it to people as cloud-based services. So basically what various companies have been doing in industry for some time. So why are we interested in doing this? Well, it's partly because the nature of science is changing. It is on auto advance, I think, although I was told it wouldn't be. So some of you may have seen a picture like this. This is the cost to sequence a single human genome. The first time a human genome was sequenced, it cost billions of dollars. By the year 2001, one could do it for roughly 100 million. The cost continued to decrease at roughly Moore's law speeds over the next several years. But then at some point, advances in technology led to a dramatic reduction in the cost of sequencing a single human genome, to the point where it is now well, it's not much more than $1,000. The slide is slightly out of date. Many people project further precipitous declines, in fact. And so that the cost will get into the sub-$1,000, perhaps even just hundreds of dollars. Similar things, of course, are happening in many other fields of science. Data, which used to be scarce, is suddenly becoming plentiful. And this, of course, results in tremendous opportunities. People are expecting transformations in our understanding of many fields of science, transformations in the nature of clinical care, and so forth, thanks to this data. The only problem is these large quantities of data are not easily manageable by your typical research lab. So the human genome, the first one, was obtained via a multi-billion-dollar, hundreds of person, tens of institutions collaboration. Most science, most clinical care, most research is done in small labs that will have just a PI, a few students, perhaps a few postdocs. Just to give a feeling for this. So here we have a little bit of data again. The amount of money awarded in a typical NSF research grant. This is a few years old, but the numbers have not changed, except it's, I think, got harder to get money than just 6 years ago. So most awards, 80% of awards, in fact, are less than $350,000 over 3 years, typically 3 or 4 years. 50% of grant dollars goes to those kinds of awards. So most science is being done by often incredibly smart and motivated people working in very small teams with very limited resources. So how are we going to allow these people to continue to make progress, to innovate, whether it's in genomic science, material science, understanding of the environment, etc., in an era of big data? So clearly, one solution that isn't feasible is to give every one of these researchers a dedicated engineering team, a dedicated computing infrastructure, etc. So that's the problem that science faces today. It's in many ways not that different than the problem that many companies faced, just a few years ago, when vast amounts of data started to becoming available to them from sources such as e-commerce. And I think we learned from looking at the examples of many of the companies who present here that we've learned that the solution to the only way you can allow a lot of people to do much more with the same or less resources is to apply a couple of things. First of all, automation on a large scale, so that you activities that these damn slides, so you can apply activities automatically that you might previously have done manually. And secondly, outsourcing, because however smart your washing machine might be, and however automated it might be, your ability to make progress is going to be limited by your ability to acquire those resources and then operate them, even if their actual day-to-day activities are automated. So large-scale outsourcing is essential to achieve economies of scale. So this, of course, is these two pictures are not the ones one normally uses to illustrate what the value proposition that Amazon offers to industry, but I think in a way it captures what they have been doing so successfully. So thinking about how we might achieve similar advantages or benefits in science got us to thinking about what would it mean to build out cloud-like capabilities that were intended to accelerate human activities, in this case scientific research, but focusing in on the things that made science difficult, particularly science in an era of big data. And so we talk sometimes about building a discovery cloud. And in a sense, the process that one follows in designing and building this so-called discovery cloud are not that different than the processes you follow in designing infrastructure to automate the business processes. You want to find the activities that are particularly time-consuming and that are amenable to automation and outsourcing. You want to move those activities. Well, first of all, you want to automate them. And secondly, you want to move them out of the individual research lab because they're fragile and expensive to run if they're replicated in every lab across the country. You want to deliver them instead as high-quality, low-touch software as a service. For various reasons, reliability, cost, etc., you want to leverage high-quality infrastructure as a service to actually deliver these services. And then over time, ideally, one will extract out common elements to build out a research automation platform that will deliver a set of essential functions that can be used by many different applications. And so those are some of the activities we've been engaged in for the last just a few years. So let me say a few words about where we are in this process. So we started off about 4 years ago in pursuit of this vision, focusing initially on the area of research data management. So we didn't pick this area of work blindly. We, myself, and my colleagues have been engaged in building high-quality research data management systems for quite a few years. For example, much of the software that was used to process the many petabytes of data that led to the discovery of the Higgs boson at the Large Hadron Collider was based on grid computing technologies and methods that we developed in our lab at the University of Chicago and Argonne. Big difference, though. The LHC computing grid, as they came to call it, was built by a team of hundreds over many years and was dedicated to the needs of a single scientific project. We want now to, if you like, create a research data management solution or set of solutions that will work for tens of thousands of groups and that won't require a team of hundreds to create and operate it. So one way of thinking about what we've been working on over the last few years is we've been asking, well, what would a Dropbox for science look like? So most people in this room probably use Dropbox or something like it. Certainly many people in the scientific community do. They use it to share all sorts of files, many PowerPoint and Word documents and other more interesting files, mostly files of modest size, megabytes or gigabytes, not typically terabytes or petabytes. So a Dropbox for science might let us do many of the things we do with Dropbox, plus a lot more as well, as I've listed here, but do it for really big data. It would do it for data that was measured in the terabytes or increasingly the petabytes in size. Data that perhaps you don't want so much to replicate on your workstation and some cloud storage system, but placed somewhere where it can be very carefully managed and shared with other participants in your projects, while also allowing you to automate many of the other processes that are associated with research data management. So this picture here sort of captures some of the work processes that characterize a lot of modern science. So I've got a couple of scientific instruments here. This is this beautiful picture, if you can see it, is the Advanced Photon Source at Argonne National Lab. It's a very high brilliance X-ray source that's used to illuminate, all sorts of materials, biological samples, and so forth, generating terabytes of data that reveals information about the internal structure of those materials. This is a sequencing machine down the bottom. Both of them in science would be used to produce, used to be megabytes, now it's terabytes of data. And this data typically flows through reasonably complex workflows and business processes, if you can call them that, as it is translated into community resources and into scientific knowledge. So in principle, it should be easy to do all these things that I list up the bottom and up the top. In practice, it's not so easy. So I don't know if those beautiful yellows show up here very well, but just sort of depict some of the challenges that a typical researcher encounters when attempting to manipulate these processes of translating data from its original point of generation via a computer-intensive and often collaborative process into new scientific discoveries. These are things that for years people have done, well, first of all using notebooks, then using PC tools, spreadsheets. Now suddenly they're struggling with doing these things because they have to perform the same task essentially with terabytes of data. So we decided to start looking at some of those time-consuming activities and see how we might automate them. And we started off with just 3 very mundane operations, if you like: moving, synchronizing, and sharing data, and decided to look at what it would mean to deliver those capabilities via a software-as-a-service model. In other words, to take the logic that's required to maneuver and manage and track and control the movement of data through these often wide area network connections, from source to sink and from collaborator to collaborator, from storage to compute engine and so forth, and basically completely automate those processes, take them completely out of the hands of the individual user. In so doing, of course, we hope to, let's go back again, please, take activities that previously might take weeks or months, literally. I mean, I've seen many labs in which some grad student is giving the task of moving data from A to B, and they spend weeks carefully shepherding that data movement process. And in other cases, allow people to undertake things that they would not otherwise be able to undertake. So the result is this system we call Globus Online. And here we will allow it to animate. Let's go back. Thank you. A cloud-hosted service, as we'll explain, it runs entirely on Amazon computers, taking advantage of many different Amazon services. It manages the task of moving data from a data source to a data destination. The data source might be a genome sequencing center, a high-energy physics experiment, a telescope somewhere, a supercomputer. The data destination might be, a large archival storage system on campus. It could be an Amazon S3 storage repository. It might be a supercomputer where analysis is going to be performed. The connections over which it moves are typically very high-speed, 10, even 100 gigabit network links. The logic that manages that movement process sits here, and this is the logic that knows how to negotiate access through firewalls, how to deal with the often rigorous security protocols that govern access to community resources, that knows how to optimize data movement so that you can get close to peak capacity of a 10 gigabit link, and more challengingly, often move data efficiently from one mass store system to another mass store system and so forth. So the user can simply hand off responsibility for performing these tasks to this Globus online service. Okay, so that's the first thing that we implemented. The second thing we've provided more recently is support for sharing as well, another, it turns out, vitally important feature for many scientists. So I produced some data. I put it onto a mass store system. It could be on an Amazon storage system, or maybe something like the National Center for Supercomputing Applications, which runs many petabytes of storage for scientists. Now I want to share it with 100 collaborators worldwide. I can't afford to require them each to get an account on that facility. So we incorporate into Globus Online identity and group management functions that let us control who's allowed to access data. And that seems to be incredibly popular with our user community. So here's another nice build. So in order to make this work well, to achieve the ease of use that Dropbox provides for storage, we do a whole bunch of things. We integrate support for a wide range of different security protocols. And the number of different security protocols that are found in the science community is quite substantial. We provide credential and group management. I'll say more about that in a minute. We put in some very sophisticated methods for managing and optimizing transfers. We build in support for automated retries. So once you ask Globus Online to move 1 million files from A to B, they will get there in the end unless there's some permanent failure in the network or storage systems that you're operating over. And then we provide, of course, the usual things you'd expect: web interfaces, REST APIs, also command line interfaces that I won't say too much about. Okay, so it's interesting. We've made this available probably about 3 years ago now for the first time. At a very small scale. Adoption has been quite astonishing. So universities, research labs, et cetera, across the US and around the world have started to adopt this as the primary means by which they move data in and out from their campus computing systems, their lab computing systems, to and from remote supercomputer facilities. So there's lots of, I won't go through these, but like NERSC is one of the largest Department of Energy supercomputers. Exceed links all of the National Science Foundation's supercomputers. Fermilab is where a lot of the high energy physics calculations are performed. So these are big national facilities that are adopting Globus Online for their use. And here's some data. So more than 12,000 registered users. We've moved more than 27 petabytes. It's accelerating fairly rapidly. More than 1 billion files. Very high availability. Despite the occasional hiccup, we've not found hiccups on our Amazon hosting platform to be a significant problem. We've achieved amazingly high availability over the last 3 years since we started hosting on the Amazon platform. So some people ask me, by the way, why we, given that I work at Argonne National Lab, which is a very professional, high-quality research computing infrastructure, why don't we simply host these management services there? And the reason is simply that no research institute can provide the availability and reliability that we require. Even at Argonne, they'll take power down in our machine room building for 12 hours once a year, to upgrade power supplies, and that's that of course immediately kills one's reliability goals. Okay, so a few words about the Amazon Web Services that we use. So, well, we host the actual management logic, the logic that sits there monitoring transfers, initiating transfers, retrying transfers on EC2 instances. We use elastic load balancing to dynamically create additional instances in the event of any failure or other problems. We use the simple notification service and simple mail service to notify users of changes. We store historical data state in Amazon S3. We store active state in Postgres, a Postgres database. We will be moving to RDS Postgres now that that is available. So we make pretty heavy use of Amazon services for our purposes. So a few little examples. So these are the sorts of things that people do in this space. Move 22 terabytes of cosmology data from one lab to another. This is the sort of thing that runs incredibly smoothly, except for the network monitoring group at Los Alamos, who thought this was a denial of service attack because no one had ever moved stuff so fast over their networks before. That's quite a common problem, by the way. I just was speaking to someone from Qatar last week, and they had the same problem again, someone started using Globus Online, and they thought that their networks were under attack. A student moving close to 1 million files back and forth between two labs. I still find this next one quite impressive. Someone replicating a petabyte of data across the research networks. That took a while. I can't remember how long exactly, but it ran for several weeks, maybe even several months, but it finished without user intervention and provided them greater resilience. Also in other cases, people were using Globus Online as part of human-in-the-loop sort of operations processes. So here, data being collected at that advanced photon source that I showed you, being transmitted across the country for analysis and then being translated back to be viewed as part of the experiment design process. Okay, so this is where we are in terms of operational services. And if you go to globus.org, you can sign up and start moving data. It's really, I think, quite beautiful and easy to use. But of course, we want to do more than that. We want to address many other aspects of this research data lifecycle. And we want to do it as we have been discussing now by identifying the painful parts of the research data management process and working out how they can be outsourced, basically to run on Amazon computers. So what we've talked about so far are these parts here of the Globus platform, if you like. We have a sharing and transfer service. We have an underlying group and identity management service. We have some logic that you download and install on your workstation or your supercomputer or your archival storage system in order to allow it to participate in the Globus Online ecosystem. This represents, if you like, the software as a service part of Globus Online. But we're also starting to see people really embrace this notion of a platform for research data management. And so you'll hear more about some of these elements from in particular Globus Genomics from Ravi-Madduri in a minute, but let me say a few words about how people are using one element of this Globus Nexus. So perhaps I'm sure some of you are painfully aware of some of the challenges inherent in identity management. But in science, it's particularly difficult to deal with these problems of identity, authentication, authorization, because science is so inherently collaborative and because scientists so often participate in projects that span institutions and in a way that perhaps they didn't. So they form new teams continuously, and those teams continuously bring in new people and need to access new resources. So we see across the scientific community, as science evolves into an increasingly collaborative process, people standing up ad hoc mechanisms for assigning identities, managing profiles, organizing users into groups. And so we realized a year or so ago that we basically had built out machinery that did that pretty well for researchers. And so we created this thing called Globus Nexus, which does the following things. It can assign identities to you. Stop, okay. assign identities to people. It can map those identities, link them with other identities. For example, a Google identity, a campus credential. It can allow users to manage and create groups and create profiles. And then we sort of started talking to people in science who we saw struggling with problems of identity and group management, and said, hey, we can take those problems off your hands, and said, you can outsource identity, group, and profile management to us. And what we found is that a growing number of people are doing exactly that. This is a few of the sites that have chosen to outsource identity and group management to us. So the National Science Foundation Supercomputer Federation, the Open Science Grid, another large physics collaboration, various universities, Department of Energy, K-Base, which is the systems biology and knowledge base project. They have 1,000 or so participants across the US, and they get their identities and groups from us, and so on and so forth. Okay, so there's K-Base again. This is one of the US's largest supercomputers. The Earth System Grid distributes large amounts of climate data to tens of thousands of people around the world. The Globus Genomics system that you'll hear a bit more about in a minute from Ravi-Madduri. And then finally, maybe I'll just say a few words about where we're going after this. So this all exists. People are using it. Thousands of people, in fact, more than 12,000 people. But of course, we're trying to go further. And so the next thing we observe that people want to do when they can share data, they can move data, they can share data, then they want to be able to keep track of it, annotate it. A lot of science is really involved is the process of making notes about the data you've got and the connections that may exist between one piece of data and another. So we're adding in a set of what we call data set services. So here's one way of thinking about what we're doing. Imagine a Dropbox that doesn't just replicate data, but actively extracts metadata from files as they're shared. I guess Flickr does that sort of, or used to do it. Extracting metadata from photos. We want to do that for all scientific data. Create catalogs, virtual views of data based on that metadata or other metadata, and then be able to invoke computations on sets of data. And the next thing we're going to talk about here is, in fact, an example of a system we're building that can do exactly do that, can compute on large amounts of data. So, Mr. Madduri.
Thank you, Ian. This is okay? Okay. Let me just exit the show and turn off the auto at once real quick. Okay. Okay, that's good. My name is Ravi-Madduri. I'm a research fellow at University of Chicago at the Computation Institute and project manager at Argonne National Laboratory. I'm gonna continue the theme that Ian is building on and use that to talk about a particular science, a particular scientific application that we're developing to make it really easy for researchers to analyze large amounts of sequence data without having them to build their own IT infrastructure to do that. So I'm going to talk about Globus Genomics, and one thing I wanted to say in order to get attention of people in the audience is to kind of talk about what we have achieved so far. This is the pricing that we have to analyze next-gen sequencing data using Globus Genomics, and we've been able to do or offer this service to researchers to analyze a whole exome for $5 to $30, and a whole genome with under $100, and do RNA-seq analysis with from $5 to $10, and For people in audience who understand next-gen sequencing and its impact in finding the cure for diseases like autism and type 2 diabetes, understand how powerful this is. This means that researchers who are working on finding cure for diseases like cancer and type 2 diabetes no longer have to worry about the cost it takes to analyze large amounts of sequence data that they've been acquiring. So to some extent, the cost of doing or analyzing the sequence data is the rate at which it's going down will accelerate the rate at which researchers can find actionable biomarkers for diseases cure of the diseases. So so this is the price points that we offer the service today. But as we continuously innovate in making our analysis much more efficient, and thanks to a lot of new Amazon instances that get announced what seems to be like every 6 months, we can bring these prices down even more. So you can imagine doing a whole genome analysis at less than $100. You know, what would that mean? Would that mean that, you know, people who are doing research in cancer and type 2 diabetes can get more data, can analyze it at much faster rate, and be able to find therapeutics for those diseases very quickly? So this is something that we're quite excited about, and we want to keep pushing the envelope on lowering the cost and increasing the efficiencies of running these analyses for researchers. So that's the goal for Globus Genomics, and I'm quite excited to kind of talk about that in more detail. So what I'm going to talk about is I'm going to build upon the vision that Ian laid out on Globus Online, and kind of give you a little bit of intro about how we came about this sequencing analysis, and what does that mean to, how does it relate to big data management, and then talk about the approach we are taking in Globus Genomics, and then take some questions and turn it over to Ian actually to close to kind of give the closing remarks. So as Ian talked about, the goal of Globus Online, the Globus vision is to accelerate the rate at which researchers do their discoveries. And one of the things that we are working on is to make research IT be available as a service. And the idea is that if we can provide these research data management services, research analysis services for researchers managing big data as a service, how would that impact, how would that affect the rate at which discoveries are made? And this is a great quote that Ian and I use in our slides, is that the civilization, human civilization advances when people do a lot of actions without thinking about them. So we're hoping to build services, we're hoping to build data management and analysis services where researchers can do large-scale analysis and data management without thinking about them. So you could see how this could accelerate the pace of discovery. So we started working in the sequencing analysis a year ago, and we looked at the domain of next-gen sequencing domain. And one of the things that we realized is that a lot of data that gets generated in sequencing centers by researchers get moved. Researchers get them by FedEx. So FedEx is a mechanism where sequencing centers send this data to researchers, and then if the researchers want to collaborate, and researchers do collaborate because all the discoveries that are being made recently are all team efforts, and when researchers try to collaborate with each other, they move the data sets to each other's institutions using protocols like FTP or CP. They'll set up an FTP server, put all their data there, and give a username and password to their collaborators. And this is all great. The only thing that is wrong about using these protocols is that FTP and SCP are designed for internet that was at least 15 to 20 years old, when the networks were not this fast and the pipes were not this big. So they introduce a lot of they introduce a lot of pain, and they take a lot of time to move large amounts of data. And when you actually want to analyze this data, the researchers have to move this data to their clusters, and again, you have a lot of inefficiencies and a lot of time spent in essentially moving data, managing data all the time. And when you move to, so once you have the data moved to a place where you can actually analyze it, then the analysis involves, so I just took an example of a pipeline that's very popular in genomics to call variants in the raw sequence data. And researchers typically, if they want to do this analysis, shell scripting is their friend, and you see a lot of bioinformaticians, a lot of biologists becoming hackers, becoming computer science people, writing these shell scripts that are analyzing this data. While this is, it's not necessarily a bad thing for people to learn how to write Unix shell scripts, but what they do, if you look more closely as to what the researchers and the postdocs are actually doing, is that they're manually moving this data to where they can compute. And then they're installing all the tools that are required to do this analysis, and they're managing all the dependencies among all these tools, and they're writing these shell scripts to sequentially analyze these large data sets that they have just moved. Again, it's not necessarily a bad thing, but it's highly inefficient because it's very manual, it's very error prone, and chances are they're not taking advantage of the fact that the underlying machine that they're running their analysis is a 32-core machine, and they're running their analysis on just one core. So there are a lot of inefficiencies in the way that the research gets done, especially in the area of next-gen sequencing. And one other thing that I point out here to all my colleagues in universities and academia is that people leave teams all the time. Postdocs get better positions, they become assistant professors, they move on to, so people move on from the groups that they're originally part of. And when they move, they actually take all their knowledge with them. So the researcher, the principal investigator doing the research, once a senior postdoc leaves the group, this research comes to a standstill until they hire a next postdoc who builds the whole pipelines, whole scripts again from scratch, because he can understand. We all know that if one person develops a shell script, chances are the other person using it are fairly minimal. So people rewrite a lot of the script. So it's very hard and difficult to maintain, to transfer the knowledge from one person to another person, and to have the continuity of the research in the sequencing analysis in research labs. So we looked at these two problems where the issues in data management, data moving, and analysis, and we thought that we could really bring the capability of Globus Online and Amazon Web Services together and build a service that could be very useful for researchers. So we built Globus Genomics, and one of the first things we have done, or we're still doing this actively, is to get FedEx out of this equation and FTP out of this equation, and use Globus Online to move data using the wide area transfer network that provides a fault-tolerant, reliable data movement across multiple endpoints. So our goal is to connect all these sequencing centers, like Broad Institute, for example. Researchers get the their sequencing data from a variety of places, and we want to work with these centers, and we do work with them already, and set up Globus Online endpoints, and we move the data using the wide area network using good FTP, which provides a high performance, fault tolerant, and secure data transfer mechanism to reliably move the data. And then we connected this data management platform with a workflow platform called Galaxy, which is a open source web-based workflow management tool that is quite popular in next-gen sequencing analysis community, where researchers who use Globus Genomics can go to, can use a web browser, go to Globus Genomics, and type in Broad Institute's Globus Online endpoint and authenticate to that institute's that endpoint and transfer the data that Broad has generated for their samples into Globus Genomics using Globus Online, and use one of the pipelines that we created to do the analysis at scale on the cloud. So what we've done is we have created a set of computationally efficient analysis to do exome and whole genome and RNA-seq analysis, and we run them at scale on Amazon instances. So, so the goal is that researchers who are doing large-scale genomics analysis and getting their sequencing data from these genome centers can use Globus Genomics to reliably move large amounts of data into Amazon and do the analysis at scale, build the pipelines using Galaxy framework, and run them at scale using Amazon's infrastructure. So this is how we went about building Globus Genomics. We have, as I said before, we have various endpoints set up at various sequencing centers, Perkin-Elmer, Broad Institute, and Illumina. We're working with them in setting up a Globus Online endpoint. So researchers who have data generated there so that's one big part of the data management part. And then we have the Globus Genomics service itself running on Amazon resources that consists of all these components. We use Globus Transfer to move data. We use Galaxy to manage and create workflows. And for identity management, we leverage Globus Nexus that Ian talked about. And we run this analysis by creating on-demand clusters and manage them using Condor, the HT Condor framework developed from University of Wisconsin-Madison. And we have some secret sauce in provisioning these instances to get the maximum bang for the buck, to lower to do large-scale analysis using various types of instances that Amazon provides. And then we kind of build this dynamic worker pool based on the demand. So when a researcher, typically in our experience, researchers get a batch of exomes or batch of data that they have to analyze, and they would like to leverage the service and only pay for what they're using. So we build a dynamic worker pool to match the type of analysis that the researchers are doing. So this is how we built Globus Genomics. We have, I'll talk more about the kind of the innovations that we have done in doing the next-gen sequencing analysis, what we have done to lower the cost and increase the performance and reliability of doing this analysis. So one such example is this. So this is a graph that for the month of October as to how many spot instances, how much usage, how much analysis has been done on Globus Genomics, and the price that we were paying for the spot instances. As you can see, there's one day where we were running around 420 instances on one day, and we were paying a lot of we're paying quite a bit of money on the spot instances. And only yesterday I realized why we were paying that much more of money on spot. Thanks to Cycle Computing's petaflop challenge, they were using up a lot of spot instances that drove up the prices in spot, and it ended up costing us a lot more than we originally anticipated. But as you can see, there's a steady state that allowed us to come up with the price that I talked about. In the last 6 months, we've been working with a dozen of research groups across the country, and we've so far used around 350,000 core hours on Amazon Spot instances doing next-gen sequencing analysis. And one of the things that I'm excited about is that all of this work resulted in some pretty nice and useful results. One such result is this. We worked with a group at University of Chicago that works in autism research, and they have acquired 4 terabytes of data of trios of exomes of a mom, mother, father, and the child. The child is diagnosed with autism, and they want to do large-scale analysis on figuring out how the child's exome is different from mother and father. So we created a high-performance reusable pipeline on Globus Genomics that would take this raw data and would run this analysis at scale on all of these 4 terabytes of data. And then once we have run it on real data, the researchers were able to make real discoveries and were able to find biomarkers that they were planning to use to create therapeutics for a set that show very good promise. So we recently had a paper accepted at the International Society for Autism Research that kind of recognized the findings that these researchers have made in using this pipeline. So there are a couple of things I wanted to talk about here. One is that this pipeline is reusable, because once we spent over 6 months working on creating this pipeline with the leading research group in the world. Now, because of this pipeline is available in Globus Genomics, all the researchers who are working in anything to do with genetic diseases can leverage this pipeline. And this is a great way of advancing the science so that people don't reinvent the wheel, don't recreate. They can get a jump start in doing their analysis by leveraging the work that has been done by others before. So in Globus Genomics, in addition to using the Spot instances and other types of instances that Amazon provides us, we also build computational profiles for various analysis tools. What we do is we run a particular analysis tool, we figure out how to run it at scale using various instance types, and we create a profile for the tool, and then we use that profile to figure out the right type of instance that we can use to do this analysis. And then we use both a combination of on-demand instances and reserved and Spot instances that are provisioned on demand. And we've been using Gluster as a shared file system that gets distributed across head nodes and the compute nodes. And one of the things that Amazon helped us understand a bit more is how to do provisioned I/O on the EBS volumes that we create. And that has been really great in improving the performance of the pipelines that we are creating. So with that, I want to kind of talk about some of the things that we're working on. In addition to just analyzing the raw data and finding the variants in this exome data sets, researchers have a lot more other data sets that they collect that need to be integrated in order to provide a end-to-end view of a particular patient. These data sets could include phenotypic information like your blood type, your blood pressure, and things like that, and combining them with the results from the next-gen sequencing analysis. So one of the projects that we're working on today, now is to integrate Globus Catalog for metadata management and integrate that with Globus Genomics. We also want to make it really easy for researchers to share their results and their pipelines with their collaborators. So we're leveraging Globus sharing in order to do that securely. So the recurring theme in my talk is that we use Globus services, we use Amazon as building blocks to build these science services to advance the rate at which discoveries are made. We're also looking at Glacier to integrate that with, so that we could provide a low-cost archiving capability to our researchers who are analyzing, who are getting multiple terabytes of data. We're looking at other computational modalities in order to get more performance out of the analysis pipelines. We have some tools that leverage MPI-based computation. So we're looking at Apache Mesos to dynamically create these clusters that use MPI or MapReduce. And one of the big costs that we have is in terms of storage. We want to be dynamically expand and contract the storage requirements for researchers. So this is something that we're excited about. We're going to use Amazon S3 or build a file system using LVM in order to do a better job at managing the cost for storage. So we have had great success in building, after we built Globus Genomics, so we saw a lot of adoption of this platform, and we thought that this is really good. Can we apply the same principles that we have used in building Globus Genomics to other scientific disciplines as well? And so we created 3 other services that I'm quite excited about. One is Globus Climate. This is a web-based analysis framework that climate researchers across the world can use to analyze, to run climate models and crop models at scale on Amazon resources. So they don't have to create or depend on their local IT infrastructure in order to do large-scale data analysis, large-scale science. Globus Proteomics is another service that we just started 6 months ago that does similar things that we do with genomics for proteomics data. And we do a lot of research. We work with cardiovascular researchers, and we have a service that would do analysis of ECG data, cardiovascular data at scale on Amazon also. And we're also working on a new service that would do material science research that would allow material science researchers to figure out how to create new materials. Again, it is a computational problem that involves a lot of data reduction steps, so we're leveraging the same framework to build a scalable service for material science researchers too. So we're quite excited about the possibilities. We're quite excited about the impact that we're going to make on scientific research in accelerating the rate at which discoveries are made. We're quite excited about how this is going to be a game changer on how research is traditionally done in the U.S. in the research world. So with that, I'm going to turn it over to Ian to kind of close it out and take any questions if you have.
Yeah, there's only 5 minutes, so we should just turn to questions, I think.
Yeah,
fine.
Sure.
So are there any questions, comments? Yeah.
So your 2 parts, I'm going to have 2 questions. The first part, in terms of the meta tagging and the cataloging, have you thought about working with the libraries who have catalogists who are familiar with that type of thing, so that general searches that might come in on university websites through the libraries will still be able to find your data? Have you thought about that? Second is a comment. Software carpentry will take care of the problem. We have to change the culture of how we teach researchers to program.
Yep.
So then that leads to the next point. With your analysts and your analytic tools, is there a way for outside researchers to contribute code base for new analytics? And is there an oversight, testing procedures, and all that other type of stuff?
So I think the answers are yes, yes, and yes. But no, so we do talk to libraries. One area of great of common interest is assigning digital object identifiers to data sets. And then the question of how you, what schema, if any, you follow to create metadata to be associated with data, I think we want to be quite open about that. So in some cases, metadata will be totally unconstrained and will be purely defined by the imagination of the researcher. In other cases, there are well-defined standard schemes, and libraries certainly have some experience with those. So I can say something about software carpentry. We've taught those courses at Chicago. They're great. I really like those guys. And I do think that nevertheless, although we should always be trying to make scientists better as programmers, tools like Galaxy and Globus Genomics that can reduce the amount of programming they have to do are often a good thing as well.
Yeah, the other part of your question was that is there a way that other researchers can contribute code? Definitely, yes. A lot of our work, I was just telling Ian and others, is that when we start working with a researcher, invariably they have their own favorite tool that we don't have in Globus Genomics, and we spend a bunch of time making that tool available in Globus Genomics, and we could use all the help that we can get. But definitely if researchers have contributions that we could use, we will definitely use it.
I think there's currently 1,000 tools that have been packaged and are distributed as part of this Globus Genomics package. And well, we didn't develop any.
Yeah.
We developed one or two, I think, right?
50
of those, okay.
Any other questions?
Yeah.
A question regarding the data transfer between local to the Amazon. And you indicated you solved the problem to transfer large data set. Technically, how do you do that? Like, do we need to direct connect from our local to Amazon?
No, no. We just leverage the regular internet, like wide area network that you have between the institution where you're transferring data from to Amazon. So there's really nothing special you need to do from the network perspective. The performance benefits that you get using GridFTP are because GridFTP can transfer multiple parallel streams. So you get better performance from that. And then GridFTP automatically negotiates, it figures out the bandwidth that you have at your disposal and uses appropriate network measurements to, network parameters to make the transfer go at a faster rate.
I understand that, but we're facing challenges right now to upload the big batch or terabyte data to S3 and no way can do it on the use a regular internet line connection.
So where is the bottleneck at your home institution?
Yeah.
Yeah. Well,
it's not only our institution, for every institution upload the huge, like a terabyte
Yeah.
data to S3 without a dedicated connection.
so the question is, were you saying that for them uploading a terabyte to S3 is challenging? It takes a very long time. I think because of I'm not sure whether it's because of the nature of your institution's connection to the internet or where the bottleneck lies exactly.
I'm thinking if you try yourself, but any institution just using regular,
Right.
regular internet, one connection,
Yeah.
and just through it, to S3, it takes you days to upload
Yeah.
the terabyte data.
So what's your experience with uploading a terabyte?
Yeah, so a lot of the universities that we work with are very well connected to the outside world, the internet too, and we were able to get a terabyte of data uploaded in a couple of hours, but not to S3. We uploaded it to EBS. It's not a S3 bucket, but it's in Amazon, so you could put it to S3 later. But I mean, it really depends on you have to take an end-to-end view of your network, right? If last mile problems are very common in universities and everywhere really. Your university might be connected to a 10 gig network, but your lab that you're working with is probably connected to a 1 gig connection to that router. So what we do is we work with those groups. We work with the network folks, we figure out where the bottleneck is, and we kind of optimize the transfers that way. So we do that quite a bit. So if you have a particular use case, we would love to talk to you more and figure out how we can help.
Maybe one more question back here, and then, yeah.
I think it's maybe
Yeah.
So, for instance, we're having at Stanford, and we have sort of choices to make about peering, like what availability zones are going.
Yeah.
Do we do direct connect and kind of how many links and things like that? So those kinds of choices you can sort of work with us about
Yeah.
capacity planning. And,
Yeah, so I'm not actually an expert on how to connect to Amazon, but I'm aware that like Internet2 and others are working on direct connections, and sounds like you know more about it than I do.
we have multiple circuits.
Yeah.
It's almost like two big choices in a way.
Yeah.
But, so the Globus Connect server, what's the role of that?
Yeah, so Globus Online manages, allows you to request the movement of data between what we call endpoints. And an endpoint is basically it's a grid FTP server, although very nicely packaged. And we provide a couple of different packages that you can deploy in order to set up one of these endpoints. One is what we call Globus Connect server, which is something that a data center or a computer center would run. It supports multiple users and so forth. And the other is something that you can download and install on your workstation. And it runs a bit like the Dropbox agents does on your workstation or PC.
All right.
Thank you, everyone.
Thank you.
Thank you.